But now, so if I were to solve this equation, for a given problem and actually solve and get some numerical results, I can do it by solving this model. But what we are really after today is to get some physical insight into the process of dispersion. Right, so we want to know how the cross-section average concentration is spreading in the x direction. We can do that numerically by solving these equations, but if we want to get some insight, and in particular to understand why the cross-section average seems to spread diffusively, it helps now to substitute for Cm from 4a into 4b. So let me call the first equation 4a, the second 4b. Right, so substituting for Cm, we get an equation entirely in terms of the cross-section average. And that equation is going to look like this. Right, so it's just a simple substitution. I take the term involving, so if I substitute for Cm here, I get one term from the cross-section average, I take that to the other side, and the average U comes out. Okay, so far this looks like a PFR, right? A PFR model, but now you have an extra term, right, which involves this stuff over here, and you see that you will have a space derivative now acting on another space derivative. And you will have a plus sign, the two minus signs cancelling out. So you will get the average velocity squared times the cube length base spectrate number divided by 48. And the second derivative now, which looks like a diffusive term acting on the cross-section average. And this is really where the beauty of the whole averaging procedure comes out. So you see now that basically if the small p vanishes to 0 in the case of perfect radial mixing, you get the plug flow reactor, which is why we always say that a plug flow reactor model is the limit of perfect radial mixing, or alternatively the case where U actually is independent of R. Right, that we had already seen earlier, that you will get the plug flow model. But given that U depends on R in our problem, we could also get the plug flow reactor type situation for the species equation if we had perfect radial mixing or infinitely fast radial diffusion. That would be the limit of small p is 0. But when small p is small but non-zero, we get a correction, and that correction looks like an effective diffusion term. Right? So this is, remember, a diffusion like term, and this is what we would call an effective diffusion coefficient or the dispersion coefficient. Right? Really quite a beautiful result. So you see now that what I really have looks like an advection diffusion equation, but whereas earlier I had diffusion in the radial direction and advection in the x direction, when I have now obtained this effective equation for only the cross-section average, which only depends on x and time, I have a diffusion advection equation, but where advection and diffusion are in x. And this effective diffusion like term in x really represents axial dispersion, which, remember, owes its origins entirely due to the non-uniform convection. So you can see how the averaging method with perturbation theory has really given us a way to explain why dispersion, which is convective in origin, behaves effectively like diffusion in the x direction. But now to obtain a prediction, it helps to do a little bit of more analysis. So you see, like I said, this was just this part of it just looks like a PFR, the left hand side, and a PFR would just transport the mean concentration with the average velocity. So to see that explicitly, we make a transformation of variables. So we introduce a new variable zeta, which is equal to x minus the average velocity t. So it's a moving, so transformed to a moving reference frame, right? And in the moving reference frame, my equations will change. So I will write c now becomes a function of c was earlier a function of x and time, now goes to be being a function of zeta in time. Right, and I would have to use the chain rule to obtain the new equation. So for that, dou c dou x must transform to dou c dou zeta by dou x, but dou zeta by dou x is just 1, so nothing interesting happens there. But dou t of the average concentration, now working with this transformed form, I must use the chain rule, so it's the local derivative in time with c, which comes from this argument, plus following the chain rule I have dou c dou zeta dou t, right, and this is just minus u, the average u. So then the new equation, right, the new equation in the moving reference frame, right, what does that become? Well, dc dt survives, and this term gives me this term just remains as u. Let me write it down. So I have u dou c dou zeta from the advection term, and the temporal term gives me two contributions, minus u from this term here. And you can show the right hand side remains unchanged. And now these terms cancel off. So what I have left with is a pure diffusion equation. So I get just a diffusion equation in the moving frame. So where if I move with the average concentration, so what this tells me is if I insert a slug of solute into a pipe, and then I move my camera, let's say, or my measurement device, if I move it along the tube with the average velocity of the flow, what I will see is that initial slug is going to follow just the simple diffusion equation I have here. Right, the cross section average concentration is going to follow the following diffusion equation. Where the effective diffusion coefficient or the dispersion coefficient is the average velocity squared, the square is outside, times the longitudinal Peclet number divided by 48. Right, and importantly, yes, so this is it, and this is where now we can think of an initial condition. So if I start with a pulse, so I do the pulse right, RTD experiment, right, this would correspond mathematically in the ideal situation to just a Dirac delta initial source. So I say that of x comma 0 at initial time is just a delta function in the x direction, or it's a radially uniform pulse. Then I know that I know the solution already. It's just the fundamental solution of the diffusion equation. For some reason my nib has become extremely small. Let's go to a thicker pen. Okay, so for the pulse experiment, I would have the following exact solution if I start with a Dirac delta function. It is just like I said, the fundamental solution to the diffusion equation. It is going to be essentially 1 over square root of dt into 4 pi times the exponential of minus zeta square upon 4 times dt. Okay, and the important thing to note is that this really is a Gaussian concentration profile, right? It peaks at zeta equal to 0, which in the moving frame is just the point which is moving along with the mean velocity. So you have the initial slug, which was just a spike that starts to spread about its center point, which moves with the average velocity of the flow. And the rate of spread goes as, or the standard deviation, which is square root of dt, right, increases as t to the half, which is the classic diffusive behavior. So if I were to draw it, right, as a function of zeta, initially after short times it looks like a really concentrated spike, and then with time it starts to spread out. So this spread goes as square root of dt, right, t to the half, which is like we know diffusive behavior, and the amplitude again decreases as 1 over square root of dt, as you can see here, because the total mass has to be conserved, and so on until you ultimately become uniform at very long times. Now the key thing is that the rate of spreading, as I said, is determined by the effective dispersion coefficient d, it's d effective, and this d effective is u square Peclet number by 48. But what is the Peclet number? This Peclet number, this, remember, is just right, if I go back to the definition of small p, right, small p is just u characteristic r square by L d, where here d is the molecular diffusivity. So you can see that this dispersion coefficient is inversely dependent on the molecular diffusivity. That means if the diffusivity, molecular diffusivity is higher, this d effective will be smaller and the pulse will spread much more slowly, which is exactly what we saw in our numerical experiment and what Taylor also arrived at. In fact, Taylor arrived at this result exactly because he actually arrived at the same effective equation that we have here, but he arrived at this equation based on phenomenological arguments, like I said, whereas here we arrived at this equation through an exact averaging and perturbation method procedure. And this is also the result that Aris derived by the method of moments. The utility of the method that we have used today to arrive at the same, to do the same theory and arrive at the same theoretical result, is that it can also be applied if we include a nonlinear reaction in the process to model an actual tubular reactor. This is something that we will take up in a subsequent lecture. And so the utility of this method is much broader than either Taylor's simplified argument or Aris's method of moments. Although the method of moments also has had a quite wide utility in several problems. Okay, so all it remains is for us to now, it's not ideal that we have UC sitting here. So we would like, if you would like to get a dimensional representation of the effective dispersion coefficient, all we need to do is to go back to our equation and well, substitute in the dimensional forms. So let's look at the dimensional form of the equation, of the average equation. Right, so I just go back to my average equation and again the scale of C doesn't matter, it will just cancel out. But the time scales and length scales will certainly come back into the problem. So I will get the star, where this is now these are all dimensional quantities, the average concentration in dimensional form. Right, remember this was throwing out I believe L by U, right, which will then go now to the other side, sorry, L by UC, which will go to the other side as UC by L. So I get a dou square average concentration star dou x square, sorry. Right, and this is now going to have right, I'm going to have this effective diffusion term here. Right, this is so. This will. This was, of course, non-dimensional. So to make it dimensional, I would have to write its U star divided by UC square. Right, that just comes from this term, and then I have the small p, which is UC r square by LD, and then from the other side, I also have. Right, so this would have given me upon a UC here multiplied by L, and the same would have come here, so it would be into UC by L again sitting right here. Right, so now I can cancel off these UCs, they just fall off quite nicely, and so what I'm left with now for the so the equation now is a dimensional form of an advection diffusion equation with an effective diffusion or dispersion coefficient in dimensional form. Oh, sorry. So this x star square also throws out an L square here. Right. So this L square comes from here, and that cancels with these two terms. So ultimately, all I have is the mean velocity squared times the radius squared divided by 48 into the molecular diffusivity. This is exactly Taylor's result for the dispersion coefficient of flow inside a laminar tube. Right, this is Taylor's result, which you could also write as d times the Peclet number based on the radius, which is just u r by d. So if you multiply and divide by d, you will get d times the Peclet number squared divided by 48. But yeah, this form does, I mean, it hides the d square in the denominator here. So it's important to remember that the dispersion coefficient is inversely related to the diffusivity and proportionally related as a squared of the average velocity. So the faster the flow, the more the dispersion, because after all it's a convective process. But what this tells us is that the convective process causing dispersion is counteracted by diffusivity. So the physical basis of that we'll come to in a second. Before that, it's useful to consider, suppose we had included axial diffusion, sorry. So including axial molecular diffusion, then we would have obtained the following result, which is actually very easy to see. So if you go back through our derivation now, but instead of dropping at this stage this term, right, the axial diffusion term, if we retain it, you'll see that this term after would allow us, when you do the average would just come inside the x derivatives, right? So this term would not remain unclosed. In fact, in the average equation that we have here, it would just give me on the right hand side, instead of 0, I'd have had d square by dx square of the cross section average, and that would be an r independent term. So then it would carry forward through the derivation quite simply, and in the end it would combine with this effective diffusion term as also a molecular diffusion in the x direction. So that ultimately it will just add a diffusive molecular diffusion constant to a final result. So you would obtain this is equal to d plus u star square r square by 48d. So this is actually the final full result for an axial dispersion coefficient, also accounting for the effects of molecular diffusion. Of course, this effect will be negligible compared to this if the velocity is sufficiently strong in the problem, which is typically the case in these kinds of tubular reactors. However, this term can become important, for example, in flow through porous media where the velocity is slow and the effective diffusion in the porous media can be much larger than it is in a clear fluid. But then, of course, this term is not quite right because the velocity profile in a porous media or chromatograph is not exactly parabolic. So there are changes to be made, but the essential features of the problem are same. In general, you will have the same expression, although this 48, the number 48 and the length scale to be used instead of the radius would be different. For example, in flow between flat plates, you would have the height of the plate here, but this number 48 would be different. And it's an interesting as an exercise for you to think if you just reproduce this derivation, but now for flow between flat plates, it will follow almost identically, but you will get a different number here, and it's useful to compare dispersion in a pipe versus dispersion between flat plates and seeing which one is larger. That certainly helps in understanding the physics of the dispersion problem, and I leave that to you. So before we conclude, it's useful now to try and understand physically why it is that we have this diffusivity sitting in the denominator of this effective dispersion coefficient, right here. So we saw in the numerical experiment in Fluent that if we make this molecular diffusivity large, the axial dispersion decreases. We see that the theory predicts that, and so the question is why. Right, so if we look, a little more closely at what's happening, so you start in a pipe, right? Initially we start with a slug, and then after some time, this is at, let's say, t equal to 0, at a later time t1, this slug gets distorted in this fashion, right, by the parabolic flow. Okay, so now what is the role of, remember this d here is not coming from axial diffusion, right? That is just sitting over here if we had accounted for it. The inverse dependence on molecular diffusivity which we have here is coming from radial diffusion, because that is the only process we retained in the equations to arrive at this result. So we don't have to consider the spreading in this direction, which is anyway much weaker than the overall dispersion caused by the convection. Rather, what we want to look at is the spreading in the radial direction because of diffusivity. So what you see is that while convection is stretching out the concentration or the solute slug in the x direction, right, causing a dispersion in this manner, radial diffusion is trying to make that profile uniform. So radial diffusion causes material from here to go back down, go back up, and material from here to go up, right? So it pulls material in towards the center line, takes material back towards the wall, right? Because diffusion goes from high concentration to low concentration. So the effect of diffusion would be to produce, so T1 with strong diffusivity. The same thing, but if I had strong diffusivity, would look much, it would grow much less in this fashion. It would distort much less, and it would look like a thicker but less distorted profile, right? Because as it's trying to stretch out, diffusivity prevents it from becoming non-uniform, and if the profile is non-uniform, the amount, if the slug has less non-uniformities in R, the less will it disperse by the convection. So it would look something more like this with strong diffusion. And this is exactly what we did see in our in the simulations in fluid. So although the slug itself is thinner locally at low diffusivity, it gets stretched out much more by the non-uniform velocity. Whereas with high diffusion, the slug locally looks thicker, but the extent it gets stretched out is less. So the effective spread in the x direction is much less than if you have low diffusivity and the velocity just keeps on elongating this strip. Okay, so the last thing we would like to do now is to go back and look at Taylor's original comparison of his experiments with this theoretical prediction. Those are in fact the earliest experiments. Since then, we've had numerous more confirmations from more detailed, sophisticated experiments as well as simulations. But it's really a testament to Taylor's genius and his remarkable combination of theory and experiment that essentially his original results are almost as good as anything we have today. So you see here his beautiful comparison way back in 1953. So now the open circles are his theoretical prediction as shown here. You see it has the same exponential form as we had. This is just the local position that at which he is measuring it, right? It shifted to that position. So at a certain time, 110 is the value of the position you would reach following the average velocity at the time at which he has taken this measurement. So he stopped the flow, remember, and taken a measurement at a certain time. So then the center line of the plug reaches a position 110. The spread about that center line position, which is due to axial dispersion, is given by a Gaussian profile, as we have also derived. And he matches that theoretical distribution, which is shown by the open circles, to his experiments, which are the solid black circles. And you see that there's a remarkably good agreement between experiment and theory, even with the relatively simple experiments that he has done, that he did in his paper. And so it's really one of the early, most remarkable comparisons and agreements between theory and experiments in the field of transport phenomena and fluid mechanics more broadly. And it was only in years later, of course, that, as I mentioned, the theory that he gave here was kind of heuristic. In years to follow, this theory was put on firmer footing by Aris, and then more recently by Balakotaiah using the method of averaging, which is what we have seen in today's lecture. Okay, so the take-home message from today's lecture really is that we have seen yet another powerful application of asymptotic methods. In this problem, it had to do with a limiting case where radial diffusion was much faster than axial convection. However, we saw that with the no flux boundaries, the nature of the problem was such that we couldn't obtain a direct perturbation solution. However, the procedure suggested what we have called the averaging technique, where you decompose the field into an average part and the remaining deviations from the average. And it is to obtain the deviations from the average approximately in terms of the average that we use our usual perturbation theory. And once we do that, we can represent the concentration entirely and its radial and spatial variations entirely in terms of the slow spatio-temporal variations of the average concentration. And once we do that, we have this approximate relationship. We can then substitute it into the kind of averaged equation we obtained by averaging out the original PD, and then get a model that directly describes the average concentration as a function of the axial distance and time. More broadly, this is an example of what's known as order reduction techniques, or reduced order modeling, or low dimensional modeling. And this is a very powerful, increasingly powerful and important method in today's engineering. So in many problems, the tubular reactor is one. We are interested in not knowing really all the detailed variations throughout the domain of our field of interest, let's say the concentration. What we really need to know to optimize the system or to design a better engineering system is the average concentration. So we would like to know the average conversion or the average outlet concentration from the plug flow reactor, for example. And so to design a better plug flow reactor, we just want to optimize the total conversion or the average or the RTD profile, let's say. And so to determine that and to model that and to optimize that, we don't need all the spatial temporal information that we would obtain by solving the full equations in a CFD solver. But yet in traditional techniques, we have to go through that process. We get more information that we need by solving the full PD numerically, and then we subsequently average to analyze, right? Because it's difficult to analyze or optimize using all the information that we get. So we use some sort of data reduction techniques, like the simplest case is just obtaining cross-section averages. What low dimensional modeling does is it helps us avoid the computationally intensive step of solving the full PD and then averaging the results. Instead, we directly obtain an equation for the averages that are of interest. And in this case, we've seen how such order reduction can be done using asymptotic methods based on a difference in timescales, and how most importantly that can be done in a systematic manner following the technique of averaging and perturbation methods that we've already studied in this course. So having now studied the problem of laminar dispersion, it's natural for us to consider the same method but applied to the plug flow, to the non-ideal plug flow reactor, which is something that as chemical engineers we have studied previously in reaction engineering courses. In those courses, we would have adopted or looked at non-ideal reactors empirically. So typically what's done is basically people motivate the introduction of a non-ideal dispersion type model for a PFR from really Taylor's experiments and others on laminar dispersion. But here we will see how we can obtain a precise model, in the next lecture. And most importantly, we shall see that the dispersion effects depend not only on the velocity profile and on diffusivity, but also on the kinetics of the reaction, which is why RTD done in cold flow settings without a reaction is different from the RTD done in a reactor with a reaction. And so we will see how the method of averaging can be quite powerful for the more general problem of transport with reaction in the next lecture. So with that, I thank you for your attention, and I again leave you with a possible project where you could look at repeating this calculation but for flow between flat plates, for example. And you can compare the dispersion in that configuration to the dispersion in a pipe and see what the role of geometry is in axial dispersion. So thank you, and see you in the next lecture.